Yeah, now that we're
So,
recording, I'll give a little spiel to start off. My name's Ezra. I'm covering for Hannes today. I'm a master's student in Hannes's group. And today we have the pleasure of hearing from Nicholas and Aika, who are going to be talking about their paper, Learning Equivariant Non-Local Electron Density Functionals. So with that, I'll pass it over to you guys. And yeah, feel free to get started.
yeah. So first of all, thank you for the invitation. Like you said, we are here to present our most recent research. It's a joint work with Nicholas and Stefan Günnemann. I'll be here today. Let's get into it. So first we have to start with a bit of quantum mechanics, at least a TLDR of it. Why that sort of gives an idea of the context of this work. So basically, modern chemistry is described, and reactions in modern chemistry are governed by the so-called Schrödinger equation. You see the stationary Schrödinger equation, which is basically an eigenvector equation. So if you have like an operator H, some eigenfunction phi n, and an eigenvalue En with these electron positions. As you can see, this is a rather complicated function of number of electrons, x3, many arguments. And it's a partial differential equation, which is a bit hidden here in the Hamiltonian, this linear differential operator. And the ground state is what we are interested in this work, which is characterized basically as the lowest energy eigenstate of this function. Okay, so why should anybody care about the ground state? The ground state basically tells you which chemical reactions can take place. It also tells you, for example, how proteins could fold, as you might have heard in the context of AlphaFold. And it's also important for certain, like for drug development, for example, the binding to a catalyst and unbinding and how enzymes work. So
Can I jump in with a question real quick?
yeah, sure.
I'm just wondering, so if we go back a slide, so
Mhm.
the eigenfunction that corresponds to E0, this is the lowest energy eigenstate. This is like the I guess the conformation, if that's even the right word, that has the lowest free energy. Is that how you might think of that? Kind of like is that
Uh, so here it wouldn't be free energy in a sense, right? Like free energy is like if you are sort of like in temperature above, but oh, sorry, are you using free energy like liberally or in the
Oh,
in
I'm using it very
the
liberally here. My bad. Yeah, I just
Okay,
mean like
yeah.
sort of the like
Uh,
lowest point on the kind of energy
Okay,
landscape.
yes.
so this difference. So the eigenfunctions here are associated with different energy levels, and there's like the ground state is just the lowest lying state, but they're different states for the same geometric configuration on the electronic structure. Think of like if you have LEDs that you excite electrons and then they emit in a different frequency, like emit light in a certain frequency. That's a band gap between two eigenstates, for instance, on the you have on the Schrödinger equation. But these like ground state energy refers to the lowest energetic state for a given molecular structure. So the molecular structure is the 3D position of the nuclei are fixed, and then you want to determine the specific lowest energy state, which is obviously what you typically use in the MD simulations.
Oh, I see. So the molecular structure is actually fixed, like the nuclei are fixed here, and you're just trying to resolve where the electrons are. And then my other question is just how do you interpret the other eigenfunctions that aren't the lowest one? Is there any meaning to those or no?
Yeah, like Nicholas hinted in this example of an LED, sort of like the first excited state. Like if you want to like add energy to the system, or if the system is excited, you are like limited to these like discrete steps that you can take. And for example, if you're in this LED context, if you're on an excited state, you can just like your system can be in this. This is like an allowed configuration of the system, and after some time, it might just go down to the lower state and give off a photon with the energy delta,
I
basically.
see.
And then
Okay,
you have
that
light or
makes
something
sense.
like that. Should be one
Right, right, right,
example.
right. Okay, cool. Awesome. Sorry to interrupt. Keep going.
No worries. So where are we? Yes, this brings us to sort of density functional theory, which lives in the context of this problem setting. It is an alternative description of quantum mechanics, and it puts the electron density in the center. As you can see, compared to this like equation we had before, this is only a function of a spatial coordinate which maps to a positive value. So it's a significantly simpler object. You can obtain it from this wave function simply by integrating out all except one electron position and taking the absolute square of the wave function and then just multiplying by some normalization constant in a sense. This, as we will see later, like this allows us to formulate a constraint minimization problem precisely in this context, where the ground state is characterized as the density that minimizes this so-called energy functional, which maintains the same like density model normalization. More on this later. For now, what I really want to take you away from this slide is this is a method of doing quantum mechanics which has a really preferential trade-off between computational cost and accuracy if you have a look at it in the context of alternative methods. So if you really want to do like more of density functional theory, the basis of it is really laid out by the Hohenberg-Kohn theorems, of which there are two. The first one basically just says, okay, there is a mapping between an electron density of a system to the underlying external potential due to the nuclei. And then the second states that the ground state density can really be found by minimizing an energy functional of the density and just finding the minimum, and the density that minimizes all this is the ground state energy density, ground state electron density. Getting ahead of myself. So there's a minor problem. Hohn and Kam really just didn't bother to provide this functional, which on its own makes this like a really nice theory, like we say physicists like to do, but it's not really applicable at this point. So how do we construct this energy functional? The typical approach, which is done in Kuhn-Sham density function theory, is factorizing it into a known contribution of which we have a hold of. There's an analytic expression, you can just compute it, and the so-called exchange correlation functional, which is the focus of our research. Again, really, this as a functional, it really just maps function, like a density function, to a scalar value. So what this does basically in this formulation, the exchange correlation could be interpreted basically as an energy difference between in a truly interacting system and a fictitious non-interacting system. But this is not the key point to take away from here. It's really just from a far away view. You take all the complicated stuff of interactions and quantum mechanics and you just put it into the exchange correlation function. Huh? Now we have a new problem, as you might have guessed. Okay, now we don't have a known analytical expression for the exchange correlation function. The only thing we did right was we wrote this we didn't know, and we wrote a known part of it, put it out of it, and still have this unknown that basically captures all the complexity of quantum mechanics.
So it's actually defined as just everything else. Is that?
Yes, it's really defined as just everything else. It's really just like this meme puts it quite exactly like it is. You just put everything you don't know into this term. And then you might rightfully ask, what have you gained from doing this ansatz? It's really just, you have a better posed problem in a sense, because it's comparatively small, because the known terms can already account for the majority of the energy.
Right, okay, makes sense.
And then yeah, the accuracy of this whole thing, of the whole calculations you might be doing with this functional really hinges on the accuracy of your approximation of this unknown term. So this is the first time like density functional theory came to use and popularity was when Kuhn-Sham published a paper where they actually showed like first how to express densities. So they showed basically that any electron density of really an arbitrary molecule you could pick out can be expressed in terms of these sort of orthonormal functions for this orthonormality constraint, and the density is really just obtained by summing it out. And these so-called orbitals are simultaneously, they have to solve this different kind of eigenfunction with some known term, and again, like this unknown exchange correlation energy functional. And here I have again like an eigenvalue. And these are to be interpreted as functional derivatives, which in a second we will really just discretize. Like this is the original, this is like the true theory, but in a discretization of it, you can recover like the normal derivative again. That might be more familiar to people here.
Like,
So
would it be possible to go back a slide just to, I just want to stare at this equation for a sec. So like,
this
this
one?
is some, or the one with the two functional derivatives. I just want to make sure there's kind of an intuitive consensus on what's going on here. So you're saying we have these orthogonal phi's on the right, and epsilon. What is this epsilon here? This is like an eigenvalue, or
Yeah, this is really just an eigenvalue. You can have some interpretation of this eigenvalue, but it's not the energy actually. It's really
okay.
just a constructed thing, right? Like in the end, you just take the lowest eigenvalue solutions of this, and then you can just absolute square them and sum them, and then you get the density.
I see. Okay, so in their eigenfunctions of this operator, that's the sum of these two functional derivatives. And I'm just trying to understand, like, why is this the operator that we care about? Like, why would it be meaningful to construct eigenfunctions of this thing?
This is a bit hidden here. This is really like subtle. I did a jump here. Of course, if you were to derive it, you would have to read Concham's original paper that actually tells you like what goes where.
The short summary for how you get to this point is you start essentially with the equation from the last slide where you wrote down the energy being energy of known plus function of unknown. And then you essentially take the derivative of that with respect to your coefficients of the electron density, because you wrote them in this linear coefficient of some basis functions. And then, so you take the derivative with respect to the density essentially, and then you just solve that minimization problem, and then you will end up with that equation. So in the paper, it's all written in the appendix.
Gotcha. Okay.
But here we call it short. So that's you just get this equation if you minimize the energy over the densities.
Gotcha. Okay, that's good enough for me for now. Appreciate it.
Okay, so also like which brings you back to what you just asked a bit. Like this is the discretization Nicholas was just mentioning. So typically what we do, you take these eigenfunctions and you express them in terms of atom-centered basis functions, basically. And this gives you this nice expression of the density in space in terms of a density matrix just multiplied, so vector multiplication, matrix vector multiplication with this sort of so-called density function, a density matrix. And yeah, as Nicholas also said, in this discretization, you can define a so-called Fock matrix, which reduces this initial minimization problem with regard to the density to a so-called generalized eigenvalue problem, which then is like more familiar linear algebra heavy. So two things. So if this S is really just basis set dependent and it's constant for a given basis set and a given molecule. And this is just a diagonal matrix of eigenvalues, CE. And what's hidden here, a bit in here, this F, the Fock matrix, depends on the coefficients. So this is not yet linear, which brings us to how you typically solve these types of equations, which is the so-called self-consistent field method or SCF method. So what you do is you really just make an educated guess in the beginning on your coefficients, from which you can compute a density matrix, and basically also initial electron density. Then with this density matrix, you can compute a Fock matrix, which consists again of these known terms that we brushed over, and the derivative of the functional derivative or the partial derivative of the energy exchange correlation energy with regard to the coefficient, the density matrix, which then defines this generalized eigenvalue problem, basically. So like if you first compute F and then like just plug F into here and don't only solve for C as if F was a constant of C, then you can update getting to a new coefficient matrix C, which you can then plug in, do it again and again, and then hopefully converge to a solution where F stops changing, basically. Meaning at this point it's consistent, like the coefficients that you assumed in your calculation of F are consistent with the solution of this then linear equation.
The solution is E here, right? Or
the solution is the coefficients, actually. Like we are interested in the coefficients at this point.
Okay, but so F, if I remember from the previous slides, is like a derivative of E. So F is a derivative of E, and then the thing we're solving for is, as you said, it was Oh, C. We're solving for C.
Yes.
Okay.
To give some analogy from another field which might be more aligned with computer scientists, so you can think of this as being like just an alternate optimization procedure similar to like Gaussian mixture models where you optimize over some you optimize over essentially assignments, and then you optimize over your probability distribution, and then assignments again. And you have a similar fashion here where you assume something is fixed and the perfect solution and not a free variable, and then you solve for the other variable and then iterate on that.
I see. So we want the like C fixed point of this
Exactly.
procedure. I see. Okay. All right. That makes sense.
Yeah, and it comes with no guarantees that it actually converges, but in practice it does. Or
Okay.
in sufficiently many useful applications. Okay, and then in the end, once you have your final coefficient matrix, you can really just compute the exchange collation energy density of your system. Okay, this brings us to previous work of how other people modeled these exchange collation functionals in a learnable way. So there are a couple of key challenges to modeling the exchange collation energy density, or the exchange collation energy in this case. The typical parameterization is in terms of this exchange collation energy density here, where you can really just define it as an integral over the exchange collation energy density, and then you get the energy. And here you can see like non-locality means that, okay, there might be a hidden second integral, meaning that the energy density at a given point in space could depend on a completely different point in space. This is a known physical phenomenon to exist. Like to actually capture a system, you actually have to have non-local features in your description. Another problem is energy extensivity, which is basically your the exchange collation energy density basically grows with the system size, with the number of molecules. So as you can see here, like approximately like the compound object here is the energy of that is almost the same as 2 times like the sub modules that make it up.
So wouldn't there be some interaction between the two carbons, or is
Yes,
that
of course,
kind of negligible?
that's the approximate sign, and that's precisely like this is level. It's approximately like there's a small change from here to here, but this is precisely what you need to achieve, like chemical accuracy, whether this binds or not.
I see.
But
Oh,
still,
okay.
like,
All right.
it's like on a scale of sub %.
So you
Oh,
actually
wow.
get
Okay.
the equality sign at infinite distance, because things will stop interacting. Like if you push things further and further away, if you pull all the atoms away, they will be resulting in non-interacting system. So the exact one you get at infinity, and depending on the system, they will converge exponentially through shielding effects, or they might not. If they are, for instance, ions, they will be having 1 over R decay. So the exact decay rate differs from system basis, but the general, like, if they're infinitely far apart, it's exactly equal to the sum of the parts.
So basically what Nicholas meant, like you can go continuously, of course, from the left-hand side to the right-hand side if you just like stretch this bond here.
I see.
The idea of what you wanted to convey, I guess. Okay, so what, like there are basically 2 main branches of research in existing literature of how to model this. One are local energy density models, which really just ignore that we know that there are non-local effects. So that this is like a function, or like you have this kind of double integrals, or you need to be able to model these kind of double integrals or similar functional forms by just saying, okay, we make an approximation again and say that we limit our functional space to energy densities which only depend on the density at a certain point in space and its derivatives. So this has some nice feature that these integrals allow you to really like get energy extensivity just through simple numerical methods, like the established quadrature methods. As long as you can evaluate this at any given grid point, you automatically get this extensive property of the energy. And there are known ways how these ansatz can fulfill certain physical constraints, which is linked to better extrapolation to unseen data in a sense. or it's the physicist's approach to it. Another, like as we said, this is local, and we know this cannot capture all known physical effects, like van der Waals interactions, if that makes rings a bell for some of you. Another type of research are these kernel-based methods, which are rather simple. They allow for pretty easy non-local formulation. You get a closed form solution, and there's research by Margraf, who showed how this can actually even be formulated in a size-extensive way. But it really heavily relies on these handcrafted kernel functions. So it's not really an expressive modern way of formulating this modeling task. And yeah, there's at present we don't know how to include any physical constraints into this function form. A bit of an orthogonal research topic are, like in this context, force fields. They really just try to directly learn the total molecular energy from just like this point cloud of nuclei. So it just gets the positions, the charges and the positions of the number of nuclei in an atom. And it tries to predict, and you can also like use force data in these by just taking the gradient with regard to the energy, as you know, it's a potential. So this is very compute efficient, has had a lot of success in recent years, but it's really just sort of a different use case, because here you don't model the electron density or any sort of wave function. It's really just a way to obtain forces and energies directly, but you lose a bit of expressiveness if you were interested in other, or you're not able to infer other physical observables you might be interested in if you follow this approach. So now I want to break down how we tackle the problem. So we start with just inputting the molecule here with its given electron density into our model, and we want to get out the exchange correlation energy, of course, of this electron density. First thing that we do is we get rid of the nuclei. We just really need the nuclei positions because we want to learn the density functional, and we don't need the for the exchange correlation energy, we don't need any knowledge of the nuclear charges. The next step, we have to remember it's supposed to be an exchange correlation density function. So it's really, we are interested in the density, not in the nuclei, which I think in the context of this graph learning group is a bit different to what you commonly do and how you do your node embeddings. The idea is here, we construct the node embeddings based on electron densities around the nuclei. So a valid question first on, when like we have like this continuous analytical object, the electron density, how do we input them into a neural network? Typically you do this by discretizing it on a grid. And then another key feature of this electron density is it peaks close to a nuclei, which tells us, okay, of course, this region is more important, which is also used in present like contemporary curvature methods, which have integration grids which sample also more densely on the nuclei. Just to give you an example of how such a grid might look. If that is your molecule, that's your point cloud of atoms that constitute your molecule, then the integration grid looks like this. So for our node embedding, what we do is basically we evaluate this convolution of the density with some filter function, which, yeah, for this we write out explicitly the integral. We take for given nuclei embedding, or the electron density around the nuclei, just take a nuclei position I, and then we multiply the density times some radial filter function and some spherical harmonic, which gives us these embedding type, which makes up sort of the first step in our modeling. Next, then we get like these hidden representations, these node embeddings, on which we can just do sort of spatially aware equivariant message passing to get more complex, or to learn more complex representation of the nodes and interactions. And further like non-local, like if you want to like have some tendency attacks with this one, then of course you need to have some information passed through the nodes to relate the density at this point to this point, something like that. Then to read out of this model, we have two parts. First, we use these representations to then again basically learn a spatial mask, so a bit of a reverse from the embedding part, to obtain what we call a non-local re-rated meta-GGA. So meta-GGAs are these local models that have been used before. And we really just inform it with an additional like weight correction in front that gets like this non-local feature map as an additional input.
So this GNL, so I'm looking at this first like the first thing out of the message passing module. It's like you have red going on and there's some blue there. What is this? What are these colors indicating? Yeah, I can see your mouse.
Yeah, okay. This could be just positive or negative values, for example. I mean, it's like an arbitrary like it's a scalar feature.
Right.
Basically, okay, it's actually could be a vectorial feature map, sort of. But this is just one channel of it, if you want to think of it that way, which could be positive or negative values at this point. Yeah.
I see. Okay, so and then the final, and then we have this expression up here, which is what the green is computed from, which is this function of this GNL thing, which is a function of so wait, which of these terms are explicitly using the output of this message passing layer? So is it all of them are using them?
At this point, just in this non-local reweighting factor, this is just a localized MLP. Basically, you input what you also already input in this other part of this functional and these additional non-local factors to learn really just a correction weight, which for example could be if without it, it would just always be 1. Now it could be 0.91, something like that.
Oh, I see. Sorry, and the MGGA is sort of the existing like local.
Yes, this is the existing local energy density, and we just really reweigh it in a sense by not touching this part and just adding here.
I see. Okay.
You want something to add, Nicholas?
Oh, sorry. Yeah, I was most referring to, you can imagine like how you use the nuclei features, which we use in the message passing to get to this density is essentially, you can think of, in the first step, we did this convolution to reduce the density to a point cloud. And this is just doing the inverse, taking the point cloud and mapping it back to a density. But in this case, not a scalar density, but like as Eike correctly said, like a vectorial density of features distributed in space.
It doesn't also need to it doesn't need to be a density, right? So there's no normalization. It can be negative. It's really just like
it's a feature function. It's a featurization of
on
space.
So that's true. Gotcha. Okay. So you're at the end of the day, you're augmenting this meta GGA thing that exists already and that people have done with these non-local like learned features.
Yes.
Okay. Perfect.
So if you want to like hear a bit more about some of the idea of it was like there are ways how these can fulfill physical constraints, and at least we hypothesize for now that I don't know if this fulfills some physical constraints, then we have at least if this is approximately always like at least close to 1, then one might be able to conjecture. We have to still prove it and do some like ablations or tests with it whether this is true. This might be able to sort of bias the model to physical behavior in a sense that it also generalizes better out of distribution, because then this at least exactly fulfills some physical constraints, which of course you then immediately scramble up by reweighting them with a new function.
I see. And then
they add confusion.
Okay, that makes sense. And then just like to confirm, the epsilon and the gamma here are just like MLPs that take in the original MGGA weights and then the non-local things with the MGGAs.
Yeah, so there's work by, for example, like Sebastian Dick or Nagai or some other alpha authors who basically did an MLP formulation of this part, and they showed how to include physical constraints into it, and that it helps them extrapolate well to unseen data.
Awesome. Okay, perfect. That answers my question.
So we hope to like approximately fulfill some of these constraints, but take it with a big grain of salt.
Okay.
And then the other part of the readout is really just a direct graph readout, where we just take the node features and just immediately compute some scale of it, and then do a sum pooling of it and add it to this energy density. So this is basically then the whole model that we're using, which of course immediately begs the questions, how do we perform? So first of all, we tested on MD17, which is really a data set that contains molecular dynamic trajectories of some small organic molecules like aspirin, benzene, ethanol, and the likes. And what we just see here, both we have force fields, which on their own are considerably worse than any of the density functional theory approaches, which of course you would expect because we had to do some extra physical calculation even without a good model. So as you can see, like the stick model is like one of these meta GJs that we talked about. This already outperforms, for example, these force fields alone. But then we said, okay, to give it a fair test, we do delta ML. So we did some density functional theory calculations with sort of fixed functions that are known and rather accurate, and subtracted it from the label, and then just did delta running on top of the correction with these force fields, which we considered a more fair approach. But even then, we see that this Equivariant Graph Exchange Correlation is on par, or sometimes is better. Like if, but in the end, we really just the takeaway message is this is we are able to accurately reproduce gold standard energies competing with delta ML on force fields.
Just to confirm, so oh, sorry, keep going.
No, go ahead.
I was going to ask just to so in order to get the force field that you're using for this MD, you differentiate or you differentiate through the minimizer of the energy functional. Okay. Okay.
So we have we have a numerical solver, and we really just differentiate for it, which in the literature has been termed as KS regularizer, which I think this was a paper by DeepMind, which they showed improves generalization, at least in their one-dimensional toy cases. So then after checking that we can reproduce these gold standard calculations, we tried to extrapolate to different temperatures. So we have this molecule, 3-BPa, which is just one set of molecule, and again, like molecular dynamic trajectories at different temperatures. So what we do, we train on 300 Kelvin, and then use the obtained model to evaluate on all the remaining ones. And here you see the MA, the mean relative error, mean relative absolute error, which is sort of relevant for forces in the context of physics, and then molecular dynamic simulations. And you can see, bold numbers throughout everything in machine learning.
So does this mean that a lot of these other learned force fields are overfitting to the temperatures they're being trained on in a way that KSTFT is? I'm just looking at the
it seems like it, yeah.
pain is like just going way up at 1200.
This seems sorry, what do you mean? Like what are the force fields?
So
yeah,
just
so
I guess they're all going up. Yeah,
I mean here it's like really it's just basically out of distribution, right? Like you do an out of distribution test, and these force fields, of course, they have no extra physical knowledge in a sense compared to these DFT models. So first of all, one has to be like honest, and like these are a lot more expensive, of course, than force fields. So I think it's not a surprise that if you go like far out of distribution, then of course these force fields with no internal physical bias are to perform a lot worse. But if you even go to delta ML, which is I think a really interesting case, even if you give it like a reference calculation with established non-learnable, it's sort of the same level of theory as we are basically learning here, but just with a fixed one that exists in literature, and just subtract it sort of that we get like a systematic way of subtracting energy deltas. If you then train, of course, on this data, you still see that this is like a huge performance improvement from even NACWIP, delta ML NACWIP to both. Big is doing a good improvement to that, but then again, we almost have it with this additional non-local contributions.
Right.
Maybe you need to do some more asking, I guess.
Oh, it's gonna. I was gonna ask about these betas on the bottom. Is this like some inverse temperature thing, or
That is
it's
an
like
interesting question, and we get to that on the next slide.
okay, all right, sounds good.
So yeah, what are the betas? So this is how this molecule looks like, this 3-BPA molecule. And you have these certain like angles along which you could rotate. And for example, down here, you see if you fix beta at some given angle, and then really just take along one axis, you turn around this bond, this sort of aromatic ring, and the other aromatic ring around this other bond, then you can draw these energy landscapes. And I think here you can then really appreciate fully the differences between this, what this means for MD simulations. So if you set on the left with 3D just a pure force field, you can see it gets really noisy. If you just train on like this small, I think it's at 500 samples at 300 Kelvin randomly sampled, you don't get a good representation of this force field compared to the ground truth on the very right. Then if you go to delta ML, of course, it's already a bit better informed by the underlying, by subtracting this sort of base density functional theory level of energy, but you get sort of two, see like these two minima where the ground truth only has one, which would be unphysical. This would mean like if you were to run a simulation at a low temperature, you would get like molecule that sort of clusters in this local minima, some molecules that cluster here and some here and some here. Then if you go to, for example, Dick, which is this local model by Sebastian Dick. In this local model, you already see like a qualitatively similar to the target. You have no unphysical extra minima and a reasonable energy landscape. And then, yeah, I think the difference between the rightmost is not fully visible here. They all really like qualitatively correctly predict forces basically in this context. If you like think of it as the gradient of the energy, you only have physically correct minima, at least in this subset.
Where's the target coming from? Is this like experimental or like some more expensive DFT calculation, or?
I think it's coupled class level of theory, but correct me if I'm wrong.
No, this one is with DFT level accuracy computed. I think it's some larger basis set. Like in DFT, we had this introduction of the basis set, and then the basis set you choose determines the accuracy you get, because you need more functions to approximate any arbitrary density. And then the other thing is, what you can do is like pick essentially a functional which gets more expensive and also more higher accurate. And so this one has been with a higher level DFT calculation, which includes some non-local factors through some other DFT stuff, which we I guess don't want to talk about here, but essentially non-locality ways on how previously you included non-local interactions between particles.
I see. Is this a non-learned, just like expensive
Yes.
thing, or is this? Oh, I see. So okay, so the idea of wood learning is just make it more efficient, basically. Like you could do it very expensively without any learning.
In practice, there's probably little meaning in learning another DFT functional. The end goal would be to learn very accurate data, like QMC data or experimental data, or coupled cluster data. That stuff is just, the problem with that stuff is it's usually unavailable, and fitting functions, since we are essentially just fitting functions, where that function is the function we're actually interested in, or another proxy which tells us how good we can fit a function, does not matter that much in this case. So we treat this as a proxy for learning some arbitrary functions, but in practice, you obviously want to learn very, very accurate functions and not the ones which you already can evaluate.
Right. So this has been fit on like this has been fit for 3BPA, like this system in particular.
Exactly.
Oh, I see. Oh, so the goal is to transfer these things. Okay, I see. That makes perfect sense. Okay, awesome.
Yeah, I think they're also like, if you remember the DeepMind paper, they had like a lot of reference data, but to my knowledge, they didn't publish it. Nicholas, correct me if I'm wrong.
In the DeepMind paper, don't want to make big claims on I think it's Pushing Frontiers of DFT, something is the name of the science paper from DeepMind from 2021. Back there, they did a lot of, they collected their own data. Like the issue with evaluation in density functional theory papers is frequently, or not the issue, it's a very different field. It's coming from science direction. And we are obviously coming from computer science perspective. And for us, we have typical benchmarks and like evaluate methods on same benchmarks. Whereas from a science directive, it's usually, I don't care how you got there, show me the results. And then typically in the history, people have trained functions on completely different data sets. Everybody had their own data. And then you show how accurate is it to my true data, to the nature. And that was the benchmark. Whereas for us, from a computer science perspective, we try to minimize confounding variables and isolate contributions. So this is why we had have different setups and all the other methods, because they try to evaluate different things. Yeah. There are different philosophies going on in between science and machine learning.
Yeah, but I also wanted to say with this, like, there are these huge data sets which are often, I think, are kept behind closed doors because they are very expensive to compute. Like, I don't know, Microsoft might be able to train like with a supercomputer, like a couple of these samples and use them for training something, but often they are not published. Or at least I haven't seen them. I think the DeepMind had like their own, also like some reference calculations. They were rather expensive. Yeah, but there's of course monetary interest because you could use it for drug development, stuff like that. Okay, where was I? So this brings us to, I think, the last ablation that we did in our work. How do we extrapolate to larger molecules? And we did this on a QM9 dataset, which really like contains different, like a bunch of molecules, organic molecules up to 9 heavy atoms. So really a heavy atom in this context is just anything that's not hydrogen. So water is 1, what is this? Ethene is 2, and so on. So what we did then, we asked the question, okay, what happens if we like train on smaller molecules of the set and evaluate on the larger ones? So this is how the data is distributed. So to do our splits here, what we do, we decide, okay, we train up to 5 heavy atoms. So we use them in the training validation set, and we test on 6, 7, 8, and 9 separately. So with this, we get this wonderful graphic. And as we can see, the left column says, okay, we train on up to 4 heavy atoms, which is a total of 48 molecules. Then DFT is already better than all of both delta, ML on force fields and force fields. But you can see that these smaller local models, which are a subset of our EGXC, overfits less, of course, because it also has like a lot of less parameters. But it's already at 5, which is only 174 molecules of this, I think in total 130,000. The model starts to pick up the slack and improves. And from that on forward, it's outperforming all of the remaining methods by large factors, as you can see here. Sometimes delta network gets close, but yeah, which I think brings us to Q&A, which we already did half throughout. Any more questions, any more details, any more interests, please shoot.
Yeah, anyone else in the audience have questions? Now's the time. Nicholas, I see your hands raised.
Yes, thanks a lot for the talk. I have a question on the details of, you said you differentiate through your optimization of DFT. So how do you do that? Do you use implicit differentiation, or are you using a fixed number of iterations? Or
we do it explicitly with a fixed number of iterations, which is set to be as large as necessary for essentially all the structures we had to converge, and then just normal backpropagation. So we cache all the intermediate values. We don't do fancy tricks here. That's why it requires quite a lot of memory due to the caching required for the backward propagation, like backprop. That's the name.
I see. Thank you very much.
Yeah, also if you look in the appendix, this is something we introduced this density fitting for, because there's one really large tensor that is dominating basically memory usage, which is important to represent more efficiently. But yeah, it's all in the appendix in this case when it comes to this memory stuff.
Okay, there has been a question from John that there's still a meta-GGA computation, and whereas it's, I think, training times with memory usage. So the meta-GGA in itself is rather efficient. I think the most expensive operations is evaluating the convolutions between the nuclei positions and the electron density, because that works on essentially pairwise combinations of all nuclei and every discretized point. Which you can truncate for this study, for this paper. We did not, but you can. So there's a bunch of efficiency stuff, but the meta-GGA itself is not hugely expensive, but you can, like, it depends on how you pick it, essentially. If you pick very large hidden dimensions and you have 1 million data points, 1 million spatial points you want to evaluate on, and have MLPs with hidden dimensions of 1,000, that will kill your memory. So in practice, we had very small MLPs, just as they were done in the literature, essentially. By Sebastian.
Yeah, like if you want a reference from Sebastian Dick, it's I think 4 hidden layers with 16 neurons.
So, okay, and for an E, there's a question about the computation scaling and system size. That one is in DFT typical fashion, something like n to the 4.
N to the 3, right?
N to the...
if you do smart sort of like...
it depends on how you evaluate your electron repulsion integrals.
Yeah.
It's n to the 3 or n to the 4.
There's also a question from Hugo too about DFT solutions. Did you check the resulting electron density with respect to reference computations?
That one we haven't done so far. And since there's no constraint on our model to actually give you proper densities, right? Technically, what we're optimizing for is the energy in the end after convergence should be the one from the target, but we don't do any constraints on the density. So the density is most likely not actual related to the physical density. Multimodal training and like training with target densities is obviously in the roadmap.
Yeah, also as you can see.
Yeah, sorry, keep going.
An idea was because we were looking how good can we get with energies when we compare to, for example, force fields, which could of course not use density data. That was another aspect of going down this route for this paper at least.
I was wondering about, so when you guys actually minimize this functional, it's discretized over some grid. Is this the picture you showed with the nuclei and all the like kind of points around it? Is that the grid you chose, or is it some rectangular?
No, it's really just like they are called Becker grids, or like Becker curvature, which is like an established technique of building this. So there's like a highly symmetric radial part, or how you like position points on the unit sphere. And there's so for the radial part, then it's just cross curvature or something like that.
Oh, so this was the picture that popped up earlier in the beginning.
Yeah.
Okay, perfect. Awesome.